PASEF is a method that really exploits this trapped ion mobility on top of what we can already do with the current architecture. And it's a very neat trick in running the sample so that we can get up to 10-fold increase in sequencing speed. timsTOF Pro is a novel type of instrumentation that is based on a traditional QTOF architecture, but in addition has a trapped ion mobility device in front of the traditional QTOF architecture. And this allows us to do two things. So firstly, it allows us to accumulate ions for a specific amount of time before we send them to analysis. And secondly, it allows us to separate ions by ion mobility. So this means that the ions get focused into a very narrow band of ions, which boosts our sensitivity, and it gives us additional selectivity because the ions will be separated by their collisional cross-section. diaPASEF is the next evolution of the DIA method, and it really takes the ion mobility component into DIA. And we will use diaPASEF to analyze large patient cohorts or analyze large experimental perturbations, which is required for any sort of systems biology or personalized medicine approach. So if we are able to analyze very large experimental perturbations and quantify analytes in every single perturbation, we can understand how biological systems work and how they react to perturbations and how signals are processed. On the other hand, if we apply this to individual patients and patient cohorts, we can trace the molecular profile of a single patient over long periods of time, and we can understand how the molecular profile changes over time as the environment and as individual perturbations affect that individual's life. And eventually, we will be able to observe a transition from a healthy profile to a disease profile when we see the person move towards a disease state. We are currently working on two main pillars in mass spectrometry. And the first pillar is technology development, because we realize that the current technology in mass spectrometry still needs improvement before we can address really the large-scale questions, right? Before we can go to the type of cohort sizes that we really want to address. So we spend a fair amount of time developing new software and new experimental methods in order to increase the reproducibility and the scalability of mass spectrometric methods. And at the same time, we then take these methods and apply them on the second pillar of our research program, which is based on personalized medicine, where we are trying to track longitudinally individual patients with a very dense sampling setup, so that we can see molecular profiles in patients' biofluids change over time, and we can understand how they dynamically change during the lifetime and during time periods of health and disease. And with this, we hope to understand on a personal level what drives a transition from health to disease state. Machine learning is a technique that has recently entered proteomics. Since a few years, people have been applying specifically deep learning in proteomics and also metabolomics, with the goal to skip some of the very tedious and labor-intensive steps that we currently have to do for data-independent acquisition. And one of these steps is the generation of a so-called spectral library or assay library. And we now have the first indications that it may actually be possible to completely predict these spectral libraries, which would allow us to mine DIA data much more efficiently and much more directly without relying on prior experimental evidence and prior experimental measurements that usually have to be done by data-dependent acquisition. So this allows us to disconnect this link where we always need to do data-dependent acquisition before we can do data-independent acquisition. And we can now directly go into the data-independent acquisition data.